Okay, so welcome to my channel. This is my first video, and I plan on going over topological sort in Python. And I plan on doing a bunch of videos on different coding interview patterns, or patterns in coding interview questions. So topological sort is one of them. Um, and I was actually asked a topological sort question in a Amazon interview. So it's pretty relevant. So let's talk about this. This is topological sort. Um, so given a directed graph on the topological sorting of its vertices. So if we're given, for example, an input of 4 vertices and the edges between them. So if there's a vertex, if there's a node 3, there's an edge between 3 and 2. And there's also an edge between 3 and 0, an edge between 2 and 0, an edge between 2 and 1. So we want to find a linear ordering of this graph. So if I draw out this graph, right, this would be 3. And there's an edge between 3 and 2. So I put 2 here. Okay. And, oh yeah, and there's an edge between. So, and it has to be a directed edge. In other words, you can only find there's only a valid topological sorting or linear sorting for graphs that are directed acyclic graphs. So if there's a cycle in the graph, you're not going to be able to find a linear ordering because by nature of cycles, it's going to go back and forth. So there's no true parent that we can pin down. And I'll show how we can see that in a bit. So there's 0. And so 3 goes to 0. And there's also an edge between 2 and 0, so like that. And then there's another one, 1. And there's only an edge between 2 and 1. Okay. So the basic algorithm of topological sort is you have to find all the sources, or in other words, all the nodes that have no indegrees or incoming edges. So right here, you can see that 2 has an incoming edge from 3, and 0 has an incoming edge from 3 and 2, but 3 has no incoming edge, so it's a source. So if we were to, start doing this on this graph right here, we would just do, first you would want to make a queue. You put all the sources in a queue so that you can do them in order. So you can pop them off in order because queue is a first in, first out, like a line at Disneyland. So we'll have a queue and we'll put 3 in there. So that's 3. And then you pop left. And when you go into the queue, you pop left and you look at each node in the queue, and then each node in the queue, you look at this at the children in the queue. Okay, so we're also going to have an output, which is our topological sorting output. So that's empty right now. But so you look at 3, and then you look at the child 2. Okay, and the first thing you do is you just get rid of this edge here. Okay, and so you remove the indegrees of the children. And once you remove the indegree, you can see that before there was 1 indegree, now there's no indegrees on 2. So 2 has no incoming edges. Therefore, you can add this as a source to our sources queue, right? So after that, I can add 2 here, right? And then you go to the 0, you move this in degree. But 0 still has an in degree coming from 2 here. So we don't add this to the sources yet. And after you're done looking at all the children of 3, then you can add 3 to the output and remove it entirely from the queue, like that. Okay. Then we can move on to 2, because 2 is the next one in the queue. So we simply look at the children again. 1, we take off that edge, and 1 has no more end degrees, so we can add 1 to the queue. And similarly with 0, take off this, and then we can add 0. Okay, and then you're done with the children of 2, so you can add 2 to the output. You can append it to the output. Then you look at 1 and 0, and because they have no children, you can just automatically, you can append them one at a time. Output. And then that is the entire graph, and that is a valid ordering. The one thing to keep in mind is when we were at 2, we went to 1 and then we went to 0. And you can see that was our output, 1, 0. But we could have also went to 0 and then to 1. And the order doesn't matter because there's multiple valid topological sortings of a graph. So valid outputs for this function would be 3201 and 3210. So both of those are correct. So yeah, well, that being said, let me, and this runs an O of V plus E time and V plus E space. So in order to make the topological sorting, we're gonna have to go through each, we're gonna have to process each node and each edge at least once. So, but at max 1 time for each of those, right? As long as there's no cycles. And it's V plus E space because we're also, we're holding at any given time at max all the vertices and all the edges in our adjacency list. So yeah, that's time and space. So let me write some code here. So in Python, we can use the dec or double-ended queue library. I'm also going to use default dictionary. So I like to make a node class because just seems better to store the information this way. So let's see, so self.inDegrees. So I initialize the inDegrees and the children as empty. InDegrees at 0, children are empty list. So we're going to have, for our topological sort function, vertices, which is an integer, and we'll have edges, which is a list of integer. And it will return a list of integers. I'm also gonna list typing. Okay, so first thing we want to do is check if we have vertices. If there's 0 vertices or less than 0 vertices, we just return empty. Okay, sorry about that. Okay, and then we could have our graph. So make instantiate adjacency list. Okay, so I'll make this a default dictionary with the node as the default element or the default object that gets created. That way, you know, it's already there for when I fill up the values. So for edge in edges, right, I'll have parent be the edge 0 and child be edge 1. So for each of the list of, let's see, for each, so right here is like 3 is the parent, 2 is the child. So 3, 2. And 3 is a parent, 0 is a child, 3, 0, right? So I'll do graph parent. So graph, I don't know why it's making that noise, but so graph is just a hash map. It's just a dictionary. So graph parent dot children dot append child and graph child dot in degrees plus equal 1. So for each edge, we just add the child to the list of the parent's children, and then we increment the in degrees, the number of in degrees for that child, right? So makes sense. Then we'll have a sources queue, double-ended queue, right? So in order to fill that up, we'll do for node in graph for node in graph if graph node dot in degrees equals 0, sources dot append, right? And we could have also done if not graph dot in degrees, right? Because if not, it's the same thing as saying if it is 0. Okay, so that should work. Then it's just like a regular breadth first search. So while sources, so while the queue is not empty, current equals sources pop left, right? This is when we're popping it in our double-ended queue, pop left, for child in graph current children graph child take off 1, right? And if not graph child in degrees, then that means if the in degrees is 0, which maybe it is better to put if graph child in degrees equals 0 just for reading purposes, but sources and child graph child, yeah. And then once you go through all the children, then output dot append current. And finally, before we return the output, we want to check if if the length of output equals the number of vertices. And if not, we return an empty list. Because if the length of the output does not equal the number of vertices, that means there's a cycle somewhere. And there is no valid topological sorting for a cyclic graph. But other than that, you return the output. And that should be pretty much it. So I hope that was helpful, and I hope I can do some more videos. And if there is something else confusing or not good or whatever, please let me know. Thanks. Bye.